This is the Chapter 27 homework, both conceptual questions and problems. We went over most of the conceptual questions in class, so I don't think most people should need to go over those much. Basically, if you have more arrows going out than coming in, you have positive flux. More in than out, you have negative flux. Same in and out, you have no flux, which means there's no charge enclosed. For Q5, to find the flux, you just look at the net charge that's enclosed. Same with 6. I like 6. It was kind of interesting. 7 we talked about a lot in class, so it really only depends on whether the location is enclosed within the charge or within the surface or not. If it's within the surface of the charges, no flux and no field. If it's outside, it would stay constant because we can treat that center of the balloon as the location from which the charge all comes. It's like a center of mass. Q8 and Q9 deal with those scenarios. Problems. So with this, it says that the box contains negative charge. We've got to have more negatives going in than out. Right now there's 35 in, but 40 pointing out. So we need at least 5 units pointing into the one side that doesn't have anything showing. 17, A, B, C, and D asked me to, circle charges that would allow for the flux as noted. So plus 2Q over E sub 0, plus Q over E sub 0, 0, which I could have circled plus and minus 2Q also, and then 5Q over E sub 0. For problem 24, went back a little bit to chapter 26 to figure things out in terms of this, which is the surface charge density. Then use Gauss's law down here and solve for the charge. Notice that the area cancels when we put charge in terms of charge density times area. So area cancels on both sides. 28, pretty easy, picture around the whole thing. 36, we went over in class. Field strength is based on this formula. I just simply put 0.2 meters in for that. B, I looked at the surface area at 0.2 meters because it said it was at the outside of a 40 centimeter diameter sphere. So that's the surface area of 0.2 meter radius. And then multiplied that by the field strength, since that's, again, Gauss's law right there, E times dA. And then that would also equal charge enclosed over vacuum permittivity, and that's how I get my charge. 37 I enjoyed doing because it let me think about the fact that if this outer conductor becomes negative 50, this inner point charge is plus 100. I still need negative 100 on the inside of the conductor, positive 50 on the outside of the conductor, in order for criteria to apply where anywhere within this region, this part of the donut, if you will, the electric field has to be 0 because there's no net charge enclosed. 45, E on the outside, E on the inside, so plus Q on the outer surface. Solve for the field strength there. The inside at 0 on the outside. It's based on Gauss's law. 46 we went over in class. Again, the only one that I think is really challenging is part A. So that is this. Take a look through my logic. Remember, the negatives really don't matter here because as long as I say that it's directed in, that's all that matters. And again, the same way here, I probably should I think I took away the negative here and just said directed inward because that's the net charge enclosed. So looking at Gauss's law in general and then applying to the radius r at that point. Between B and C, no field, greater than C, the net charge enclosed is positive, so it's this directed outward. So hopefully, again, that Gauss's law, something that seems complicated but can really help us understand things about electric field. And it is not nearly as frightening as it initially appears.